Welcome to this explainer. Today, we're taking a deep, fascinating journey straight into the literal core of how a computer thinks, calculates, and basically understands the entire world. When you strip away the beautiful graphics, the smooth user interfaces, and the endless apps, what you're really left with is a highly efficient, unbelievably fast math brain. So today, we're going to crack open that brain and see exactly how computer arithmetic actually works. Here's our roadmap for this explainer. We'll start with the ALU, the literal math brain. Then we'll look at making sense of integers, followed by integer arithmetic and overflow. After that, we dive into mastering floating point numbers, and we'll wrap things up with floating point math operations. All right, section 1, the ALU, the math brain. This is where the processing actually happens. Okay, let's break down this diagram. The ALU, or Arithmetic and Logic Unit, is built entirely on really simple digital logic devices, and data moves in and out of it in a very specific, orchestrated way. Operands, which are just the numbers we want to actually do the math on, are fed into the ALU through operand registers. You can think of these registers like temporary holding boxes. The processor sends control signals to tell the ALU exactly what operation to perform. The ALU crunches those numbers using simple Boolean logic, and then it pushes the final answer out into result registers. Oh, and it also outputs flags, like an overflow flag, just to alert the system if a calculation happened to exceed the physical limits of those holding boxes. And that actually brings up a really profound point from our source text. We have, in a sense, reached the core or essence of a computer when we consider the ALU. I mean, think about it. Everything else, your memory, input/output devices, even the control unit, it all basically exists just to bring data to the ALU for processing and then take the results away. Without the ALU, your computer is literally just shuffling data around with no real purpose. Moving right along to section 2, making sense of integers, or how we represent complex math with only ones and zeros. So we run into a pretty big roadblock almost instantly with computer math. We only have binary digits, zeros and ones. We don't have a magical minus sign symbol hardwired into the system. So how on earth do we represent negative numbers? Well, we essentially have two approaches. The first is sign magnitude. It's exactly how we humans think. Just reserve the leftmost bit as a sign, where 0 means positive and 1 means negative. Simple, right? But hardware absolutely hates this. It creates two completely different representations for 0, and it makes addition incredibly clunky. Then we have 2's complement representation. Now, this one is a bit awkward for humans to read, but it's this beautifully elegant mathematical shift. In 2's complement, that leftmost bit actually carries a negative weight. It completely fixes the dual zero problem and, as you'll see in a moment, makes hardware design unbelievably simple. So how do we actually pull this off? How do we create a negative number using 2's complement? It's literally just a two-step algorithm. First, take your positive binary integer and just flip every single bit. Change all the ones to zeros and all the zeros to ones. Simple enough. Second, treat that new sequence as a standard binary number and just add 1. That's the whole shebang. And the cool part is, if you run that exact same process again, it flips you right back to your original positive number. The absolute key takeaway here is that 2's complement is almost universally used in modern processors. But why? Because it means the computer doesn't need completely separate physical hardware circuits for addition and subtraction. To subtract, the computer just finds the 2's complement of a number and adds them together. It is a massive game changer that saves physical space and huge amounts of complexity on the processor chip. Section 3. Integer arithmetic and overflow. Breaking the boundaries of binary. Now, when you add in 2's complement, the process runs exactly as if the numbers were just normal, unsigned positive integers. You line them up and you add. But because our ALU relies on fixed size registers, let's say 4 bits or 8 bits, there is a hard physical limit to how massive a number can get. If you add 2 really large positive numbers together or 2 really large negative numbers together, the true mathematical answer might actually require more bits than the computer physically has available in that specific register. And that brings us to a condition we call overflow. Overflow is what happens when the result of an addition is just physically larger than can be held in the word size the system is using. When this happens, the result the computer spits out is completely wrong, so the ALU has to trigger a special hardware flag. This basically yells at the system, hey, do not trust this calculation. This geometric depiction is a brilliant way to visualize what overflow actually looks like conceptually. Look at the circle here. Imagine a 4-bit system wrapped around a standard clock face. If you start at +5 and add 4, you move clockwise. But you hit that boundary at the bottom and literally wrap around into the negative numbers. You end up at -7, which makes no sense. The golden rule for overflow is super simple. If you add 2 positive numbers and somehow get a negative result, or add 2 negative numbers and get a positive result, you have officially overflowed your physical boundaries. So what about multiplication and division? Hardware can totally do it, essentially through rapid, repetitive shifting and adding. But engineers are clever. To speed things up, they developed tricks like Booth's algorithm. Instead of painstakingly adding a number for every single 1 bit in a multiplier, Booth's algorithm scans for entire blocks of ones and uses a combination of just 1 addition and 1 subtraction for the whole block. It radically minimizes the number of hardware operations required. All right, Section 4, Mastering Floating Point Numbers, Scaling to the Microscopic and the Astronomical. So fixed-point binary math is great, but it completely fails when it comes to massive scales. Floating-point representation fixes this. It's a system that dynamically spreads out the available bits to represent a truly vast range of values. It works a lot like scientific notation. You have a significand, which is the base fraction, a base, which in computers is obviously 2, and an exponent that basically tells the radix point or the decimal point where to float. Let's dissect how this actually builds a real data structure on a standard 32-bit architecture. Over on the left, you've got a single bit purely dedicated to the sign of the number. Then you have an 8-bit biased exponent. Now, we say biased because a fixed value is subtracted from it. That clever little trick allows the computer to easily represent both positive and negative exponents without needing a whole separate sign bit just for the exponent. Finally, the remaining 23 bits make up the significand, or the fractional part of the value. Because floating point math gets incredibly complex, virtually all modern processors follow a very specific blueprint called the IEEE 754 standard, which reserves specific bit patterns for special cases. For instance, if the exponent is all zeros and the fraction is all zeros, the hardware knows that means exactly 0. But if the exponent is all ones and the fraction is 0, that is the hardware's way of literally representing infinity. Okay, get ready, because here is the truly mind-bending part of floating point math. Unlike integers, which represent perfectly even, uniform steps on a number line, floating point numbers are not evenly spaced at all. Think about it. We are still limited to the exact same total number of bit combinations, 2 to the 32nd power. So to achieve that massive range, the numbers have to be clustered incredibly close together near 0, and then they spread farther and farther apart as the values get massive. You are literally sacrificing exact precision at huge scales in order to achieve an astronomical range. Finally, Section 5, Floating Point Math Operations, Aligning the Exponents. Take a look at the equations for addition and subtraction. Before the computer can even touch the significance and add them together, the hardware has to do the heavy lifting of aligning their exponents. You can't just take a number scale to 10 to the 2nd power and add it directly to a number scale to 10 to the 3rd power. The ALU has to shift the radix point of one of those operands until both exponents match perfectly, and only then can it do the math. Multiplication and division, interestingly enough, are slightly more straightforward here because you can just add or subtract the exponents directly. Now, because these floating point numbers are so incredibly spaced out and cover such extreme ranges, software engineers constantly have to watch their backs for 3 major pitfalls. First up is exponent overflow, which is where a calculation creates a number so massive it exceeds the maximum possible exponent. Next is exponent underflow, where a fraction gets so microscopic it falls completely below the minimum exponent, and the computer just throws its hands up and approximates it as 0. And finally, rounding. Because so many real-world numbers simply fall into the giant gaps between the represented floating point values, the computer is constantly having to round its answers to the nearest available bit pattern. And all of this really boils down to the core philosophy of computer arithmetic. Everything we've unpacked today, from the basic logic gates in the ALU, to the elegance of 2's complement, to the complexities of the IEEE 754 standard, it's all an exercise in balance. It's the ultimate trade-off. We have somehow figured out how to represent a nearly infinite universe of numbers using nothing but simple switches that are either on or off, but it comes at the cost of absolute precision. We essentially trade perfect exactness for incredible speed and a vast operational range. As we wrap up this explainer, I want to leave you with something to chew on. We've seen just how physically bound our calculations are to the size of the registers, those strict 8-bit, 32-bit, or 64-bit boundaries. If binary rules physically dictate the limits of all computation, What happens to the future of digital mathematics when our scientific and data needs inevitably grow exponentially faster than our hardware's physical bit limits? Thanks so much for joining me on this deep dive into the math brain of the computer. Catch you next time.